Hi, my name's Ian Murray. I'm with the Biomedical Engineering and Assistive Technology Lab at Curtin University. I'm going to show you a couple of the projects we've been working on recently. The first one is the complete reading system for vision impaired users. This is a technology that allows us to present written information to people with vision impairment in an accessible format. It adheres to the standards for digital talking books that are used worldwide, but the main advantage is we can handle graphics, and by that I mean we can have a graphical representation, a graph, mathematical expression within the document and automatically create a description of that expression or graphic that is comprehensible to the vision impaired user. It works with several formats, both doc, Word formats, docx, PDF, etc. So here's some examples. So we've got an image here of our early prototypes, which is just a small embedded controller connected to a hardware text-to-speech engine and a keyboard to access the book and navigate the points throughout the document. To give you an idea of how it speaks, we've got an image of a mathematical expression, fairly simple one in the top right corner there, and we'll hear how that sounds.
X index 1 power k plus X index 2 power k plus X index 3 power k plus continue until X index n power k equals 0.
That is a description created only from the image. There is no human input here. There is there is optical character recognition, but there is no entry of the text itself. It's purely based on an image. Next example we have is a simple bar graph.
This is a bar chart which indicates the average price of advertisements of 5 different channels in a year. Vertical X shows $1 million. NBC channel is $172 million. ABC channel is 166. Fox channel is 120. CBS channel is 86. WB channel is $39 million.
The next project I'll talk about is our indoor navigation system for people with vision impairment. This is an infrastructure-free system that doesn't require the building owner or building managers to implement any infrastructure within their building. It discovers the environment from sensors that are on board and builds a lightweight map from that information. We can also share that information through crowdsourcing, so if one vision impaired person moves through the building, they will pick up the information that will be passed on to the next person that enters the building. Basically, it works on this sort of system. We use the mobile telephone or smartphone as a communication system for the vision impaired person, but the sensors are a separate item that we either put in the hip pocket or mount on the chest in the case of the camera system. We base this on gait analysis. Now, gait analysis is something that's been worked on for many years, but we've developed our own system and sensors that allow us to do this in a very economical, efficient manner. We can see here that we can identify from this single thigh-mounted IMU, inertial measurement unit, the various stages in the human gait stride, and it's a highly accurate method of doing so. So we'll have a look at some videos of how we've utilised this in other areas of research as well, which include cerebral palsy, neurosurgery in the case of foot drop. This video was taken in our motion analysis lab. This is a 28 camera system. We can see those cameras up on the wall with a green light to validate our inertial measurement unit sensors. And in this case we have Jenny, who is a totally blind person. She has sensors on her white cane and 3 sensors on her leg, thigh, shin and foot. She will walk down the path and we will capture the data from the inertial measurement units and also from the camera systems and make sure that the reading is correct. And from this we can tell how many steps she's taking and calculate the distance travelled, and using the magnometers we can get direction as well. This next example is a pre-operative capture of a patient with foot drop, and as we can see he's unable to lift his foot or his toes as he walks. We capture the data, we model the effect, look at the seriousness of his condition, and then we can compare it to the post-operative. And here we have someone post-operative, quite a significant improvement in his gait there. This allows the surgeons to more accurately and non-subjectively, objectively create a scale of impairment for each of their patients. And this assists with when to operate, early diagnosis, etc. The final one we have is a case of children with cerebral palsy, and in this case we are using the same sensors to capture the movement of the upper limbs to assess the treatment effectiveness of splints or other exercises that they are doing. This is a fairly simple task that the child undertakes. This is just a normal child. He doesn't actually have cerebral palsy. We use it as a test case. And they perform a particular task. We log the data from that task and compare it over time to see if there's any improvement. This also helps with early diagnosis, treatment effectiveness and other medical attributes.